we'll start off with is just basic construction of the liquid cylinder. The figure that you see here on the left is just a sketch of a portable liquid cylinder. You have an inner vessel where the cryogenic liquid is stored. Cryogenic liquids are in the 300, 350 degrees below zero range. You have the outer shell, the stainless steel shell that you touch when you see a liquid cylinder out in the field. And in between that inner shell and that outer shell is super insulation that is a very micro thin layer of film that wraps that cylinder like a cocoon, if you would, during the manufacturing process. Many layers of that super insulation. And then you also have an extremely strong vacuum. You need a high level of vacuum there. You had a gentleman by the name of James Dewar in the late 1800s had been working with cryogenic materials, and he was the one who determined that a strong vacuum on that between that cryogenic liquid and the outside temperature greatly enhanced the insulating value of that liquid against that liquid. So strong vacuum, insulating, and then you also have the coils that are needed to operate the cylinder, which we'll talk about here a little more in depth. You have also this halo, which is a protective ring on the top that would prevent anything from from falling on that cylinder, or heaven forbid, should a cylinder fall off a truck, it helps maintain the integrity of those components on the top that are the components that are the troublemakers, really, that are the things that can go wrong. It's how you operate the cylinder, but also things that can go wrong to create problems with the cylinder. It helps protect those. This figure here in the center, you see, is really just the cylinder in the flesh as a cutaway. That was a demo that somebody had made up. The bottom coils down here in the bottom 12 to 15 inches are the pressure building coils that would be used to build pressure within the cylinder. And then higher up, these are soldered between the inner shell and the outer shell. They would create the gas use. You can see here in the center the fill tube that would be used to fill the cylinder. It also has a guide in there that would be used for support of a float run. You can see over here on the right, on the lower right, a cutaway section of a different cylinder. This is showing you what they call the neck arrangement that forms what we call the knuckle on the outside part. This is where the only place on a liquid cylinder where the inner cryogenic vessel is plumbed to the outside. This is the pathway where all this plumbing for all these components here on the top, all the gas use valve, the liquid cylinder valve, the vent valve, that's all plumbed through that neck. And that's another reason why you don't ever lay a liquid cylinder down on its side, is that neck would be very vulnerable. If you fill that with liquid is quite heavy, and it will snap and crack that neck. This in the upper right will show you the super insulation. That's an old cutaway cylinder that's been poked and probed at quite a few times. But I mean, during the manufacturing process, it's many layers of that super insulation. Now, talking a little bit about DOT 4L design and the categories of different cylinders, this is kind of important. So you have the halo that we talked about to protect the upper components on the cylinder. Well, then there's a support bracket that supports that halo, and we call that the stanchion. And on the stanchion will be somewhere, there will be a nameplate that is attached to that. And that nameplate will tell you the DOT rating of that cylinder. And it'll say DOT, which stands for Department of Transportation, 4L, which is for liquid. It may have a TC4LM, which is Transport Canada. It's the DOT version of Canada that will set up the design parameters of that cylinder. There is a Code of Federal Regulations 49 CFR that talks about liquid cylinder design and design criteria. You can get into it quite heavy if you want to. any of you with insomnia could read that at night. But this DOT classification will set up the basic parameters of the cylinder. What I mean by that is look at the chart here in the center, the bottom. 4 classifications that are common sold in the United States today: DOT 4L100, 200, 292, and 412. These last 3 digits, an example here, the DOT 4L100, 2 times that number will set up the burst pressure of that inner vessel. So 2 times 100 is 200. You can see the rupture rating of that inner vessel is 200. Same with the DOT 4L200. 2 times the 200, it's going to set up the rupture rating of that inner vessel at 400 PSI. It also sets up the maximum pressure relief valve, the maximum allowable working pressure of that vessel, the service pressure we'll call it. And it's 1.25 times that DOT number minus 15 PSI for the vacuum, 14.7 PSI, which is atmospheric pressure at sea level, really strong vacuum. They'll deduct 15 PSI off that cylinder for the pressure being seen by a strong vacuum to come up with the maximum relief valve. So 1.25 times 100 would be 125 minus 15 PSI gives you the maximum service pressure of 110 PSI. Same on the 200 is a 235. The 292 would get set up to 350. The DOT 412, which we call laser sills, would set up 500 PSI. You know, then to that, the manufacturers have their different pressure builder settings and functions that would go along with that. Common one here is a DOT 4L200 that would have pressure builder typically set at 125 with an economizer function at 140. We'll get into that in a little bit of future slides of how those work. So, you know, a cylinder, if it doesn't have that nameplate, you can't legally fill it and put it on a truck. You need to get it renameplated. You need to go back to the OEM and determine the serial number of the vessel. There's ways that you can determine that, varies by the age of the cylinder, et cetera, and then get a new nameplate issued. Now, a little bit on cylinder types. The cylinders that you see here, like the ones on the left, are what we would call a foot ring design. They don't have casters on them. They have like a rubber type big grommet, if you would, at the bottom that helps with shock absorption. But and then the cylinders on the right would be that's a round base wheeled cylinder, typically in a 230 liter to 265 liter would be the wheeled cylinders. The foot ring designs would vary a little bit by manufacturer and age, but commonly now it's like a 160 liter to like a 200 liter would have the foot ring design. Typically these are 20-inch diameter cylinders. The wheel-based cylinders today are 26-inch diameter cylinders. Almost all, I think all manufacturers today follow those standards and guidelines. Now a little bit about some of the applications. So a DOT 4L100 cylinder is what we would classify as a liquid use only cylinder. There is no gas use function out of a DOT 4L100. You know, typically comes with a 22 PSI, but you can go up in the relief all the way up to 110 PSI on the safety. Common application would be for medical, maybe in a 50 to 75 PSI range. You could use that to transfer liquid oxygen into portable liquid cylinders, commonly referred to as like liberators. You know, the medium pressure cylinders, DOT 4L200 is a 125 PSI gas use application cylinder, works in a 125 to 140 range, and then has a relief valve set at 235. The DOT 4L292, primarily a gas use cylinder, 350 PSI is the maximum safety, typically works in a 300 to 315 PSI range. And then you have what they call a very high pressure cylinder, DOT 4L412. I mean, the common application is a laser shielding gas use application. 500 PSI is the maximum relief valve. It usually works in a 400 to 475 range, depending on make and model, setup of the pressure builder system. Now a little bit about tare weight. On that nameplate that we had talked about, there will be stamped a weight of the cylinder, and that is the dry weight of the liquid cylinder with no product in it whatsoever. So it should be something as simple as once the cylinder is manufactured, they weigh it, they stamp it with that weight on the nameplate. And if that varies with any significant value, you really shouldn't be filling that cylinder. You can see this photo in the lower left here. This was a customer-owned cylinder where they had taken a square base cylinder and added fork tubes to it. I mean, it's a nice idea, yeah, but it changed the tare weight by like 80 pounds. So legally, you can't fill that and put it on the truck because you're not really sure exactly what's in there because that's not what's stamped on the nameplate. So the total weight going on the truck is going to be the tare weight plus the weight of the liquid that goes inside. Now, the weight of the liquid can vary greatly based on the liquid that you're putting in. I mean, atmospheric gases, nitrogen, oxygen, argon, and then, you know, CO2, which is not an atmospheric gas, but it's another CO2 that you can put in. That their weights are, the specific densities of these gases vary greatly. So you can see here that 201 liters of nitrogen weighs 359 pounds, but the exact same volume of argon would weigh 624 pounds. So the total weight going on the truck would be the tare weight stamped on that nameplate plus the weight of the product that you put in it. So, you know, you should be filling these cylinders by weight. So if there's residual product left over in the cylinder, you'll know what that weighs. You'll see it go on the scale. You know what the tare weight is. You know what the scale is reading, so you know how much product is in it. You'd add the additional product to where it's at its maximum fill weight based on the fill charts your company uses in the fill room. Now, a critical point that I want to point out here is that the volumes of liquid that you can store in a given size liquid cylinder will vary based on the DOT or the pressure rating, maximum pressure ratings of that cylinder. Example I have down here is a 240 liter Taylor Wharton DOT 4L medium pressure cylinder holds 382 pounds of nitrogen, whereas the exact same cylinder in a higher pressure rating DOT 4L 292 will hold 359 pounds. Now, you know, why is that important? Well, it can become a problem area where, say, you took over an account and it's a liquid use application, and the customer who had it before you took the account over used a DOT 4L 100 cylinder that they had for liquid applications, but you didn't have a high pressure, or you didn't have a low pressure cylinder to send them. You sent them a DOT 4L 200 or a 292 with a 22 PSI relief valve on it, which is, you know, a common practice. Well, that distance from the top of that inner vessel to the level of the liquid varies based on the pressure rating of the cylinder. So your customer could say, well, you know, Joe Blow used to bring me a cylinder and it lasted longer than your cylinder did. Well, that reason could be is you're using a different cylinder type and you have less liquid that you're delivering. That level of that liquid is determined by the length of the vent tricock tube that projects inside of that cylinder. That tricock, that bottom of that tricock tube varies based on the cylinder design. And that's to allow this distance inside of here to be greater. The higher the pressure, the greater that distance needs to be in there to allow for the expansion of the liquid and for the proper building of pressure in that upper part of that upper chamber of that vessel. So that's just an important thing to know between the different pressure ratings that your liquid levels will vary. And you can see all of that on the fill charts that the manufacturers have. And you can get over that hump if you want to fill it with different levels of liquid, if so long as you have the proper safety that goes with the volume of liquid that you want to put in there. You'll see charts and Taylor Wharton fill charts they will give you for your cylinder design different levels based on pressure ranges of the pressure settings. So you could turn that tricock vent tube off and fill it to a higher level and put that truck on a tank, or that tank on a truck, and ship it over the road with that higher level of liquid in it, and as long as you had the 22 psi safety on it. And they used it, you know, that way. So that's perfectly legal. Liquid cylinders can be quite heavy. So you know, this chart here on the bottom shows you that you know, for common designs like the 180 liter foot ring design can go, you know, 600 to 800 pounds depending on what liquid you put in it, full of liquid. So I mean, and a 230, 240 liter can go close to a half a ton. 265 goes even over a half a ton on weight. So these cylinders are heavy. The product that goes in them is quite heavy. So you need to be, you know, communicating your SOP procedures down to your end users so they handle your liquid cylinders properly and take care of them properly. You know, foot ring design cylinders, you should be using a hand cart. I know a lot of people roll them by the halos. That's not really recommended. If you're going to rig a cylinder and lift a cylinder, there's a proper way of doing that through the holes that are in those stanchion brackets that we talked about. You can get a J hook and put them in there, or you know how you would thread your webbing through there. If you thread your webbing through the halo and try to pick it up just by the halo, you can bend those units up like a taco shell, if you would, and render them inoperable. We have to send them out and get them repaired. So now a little bit about cylinder operation. You can see the figure 1 and 2. These are low pressure cylinders, DOT 4L100. The figure 1 would be like a foot ring design, low pressure cylinder. Notice there is no gas use circuit. It's just a vent and a liquid output out of the cylinder. And then of course your tree here that has your gauge and your relief valve and your burst disc on it. That's common to every cylinder. But then figure 2 would be the same cylinder, except in like a 240 liter, 230, 240 liter design that would have a pressure builder on it. So that's pretty common. Figure 3 would show you like a gas use cylinder, a DOT 4L200 or a 292. We're showing you obviously the Taylor Wharton design because that's what we sell and represent as Taylor Wharton cylinders. This is their common plumbing arrangement for what we call a pressure builder economizer combination unit, as opposed to 2 separate regulators that you may see on older designs. They all do the same functionality. But this magenta colored valve here would be the pressure building valve that you would turn on to build pressure. If you had a chart with a liquid cylinder control manifold, they refer to as the LCCM. That would be in the lower right-hand photo over here. This handle here would be the pressure builder handle that you would turn on. That's highlighted with the arrow here. So now we want to build pressure. Let's get pressure building in the cylinder. Well, this schematic will show you those coils that we showed you earlier in the cutaway sections in the bottom 12 to 15 inches. They are soldered to that outer shell. So you have the inner liquid, the vessel that's inside of this cylinder that's 300 to 350 degrees below zero, depending on the liquid type. And you have that column of liquid in there. That column of liquid is heavy. You would open up that pressure builder valve and liquid would draw through those tubes and hit those coils on the bottom 12 to 15 inches. And because that liquid is very cold inside, it's, as we'd said, quite 350 degrees below zero, and the ambient temperature, I don't care if you're even in Alaska or the North Pole and it's, you know, 40 or 50 degrees below zero, it's still warmer than that liquid, and that liquid will flash into gas. That gas will flow through that regulator in the top part of the cylinder, and through a Venturi type process will start to build pressure. That pressure will get delivered into the upper part of that cylinder, and it will push down on that column of liquid. And it will continue doing that until the pressure builder reaches its set value. So example would be a DOT 4L200, we said the pressure builder setting was 125. So it'll build pressure till it reaches 125, and then it will stop building pressure. Then the other economizer will kick in a little bit later. But let's talk about, now I'm building pressure in here, and now I want to get gas out of the cylinder. So I've built pressure. I'm up to my 125. The gauge is reading 125. Let's draw some gas out of here. Well, same type of function where you have these coils that are soldered to the shell upper region of the cylinder, and you would open up that gas use valve, and you have that pressure that's built up in the cylinder. It's a pressure differential to the outside. That liquid would flow through those coils, that they would get the ambient temperature. They would flash into gas, and that gas would then flow out of that cylinder. That liquid would convert to gas, flow out that gas output. Now, liquid cylinder, I mean, you use liquid cylinders because it's roughly, like a 13-to-1 ratio on a 240-liter design versus 300 cubic foot cylinder. So, it's a high gas use customer that you're sending a liquid cylinder to. You don't want to keep running them, truckloads of cylinders a week. You would run them a few liquid cylinders, but it's a use it or lose it type thing, right? That liquid's in there, it's boiling off all the time. But you've got to be able to use that gas. Well, this gas output on this particular design cylinder is going to give you around 350 cubic feet an hour downhill with a tailwind on a good day. As a rule of thumb, you get that 350 cubic foot out of cylinder. And I don't care if it's a 200 or 292, that flow, that volume of flow is always considered like a maximum threshold. Chart, Taylor Wharton, BTIC, I don't care. They're all about the same. They use the same tubing, same components. They all flow around the same amount. And, if you need additional gas output, you can go back to using a liquid and an ambient vaporizer. But that's how you would get gas out of a cylinder. Now, where's the economizer function coming in? Well, I'm in a gas use application. I'm using gas. I have my pressure builder working. I'm building pressure in the cylinder. Now, as we said, that liquid is cold. It's boiling off. You can build pressure above the pressure builder setting, and it will steadily increase depending on how you're using and how much gas you're drawing out of that cylinder. So when it will reach a higher level, and when it reaches the setting of the economizer, which, going back to the example I used of a DOT 4L200 that had the pressure builder set to 125, the economizer function is set to 140. So the pressure builder building pressure in that cylinder till it reached 125. And then he said, stop building pressure. But the pressure will continue. That liquid's boiling off. It'll build pressure in that cylinder. And then the economizer function was set to 140. When the economizer sees 140, it's designed to open, and it will open and then bypass, instead of putting it into that upper chamber of the cylinder and building pressure, it puts it back into the gas use circuit. So now you're drawing out of the gas use circuit, should lower and temper the cylinder a little bit. It's kind of like the yin and the yang, right? The pressure builder builds, the economizer, and then it stops, and the economizer opens and helps regulate the pressure. So it's really designed to try to keep that cylinder working in that range, in that zone. The pressure relief valve is there just to prevent overpressurization. It'll kick in and keep the cylinder from being overpressurized. There is a secondary burst disc there. Should something go wrong, that'll dump all the pressure out of the cylinder to prevent that cylinder from being overpressurized. Now, on a liquid application, it works, very, very similar to like a siphon tube in a high pressure cylinder, right? So you have that liquid fill line that's in there, and you would open up the valve here. Here'd be the liquid use valve, as you see on the upper right. You would draw that valve. There's a pressure differential between the inside of the cylinder and the outside, and that liquid would flow through that siphon tube and deliver you liquid at some pressure, whatever the cylinder is set up for pressure. There's also a vent line in there that you'd see on the lower right, that valve there, which is that tricock that we talked about, that extends into that upper region of the cylinder. You can open that vent and blow all the pressure out of the cylinder. You know, that would be used to drop the pressure down if you wanted to work on the cylinder, or you know, you wanted to make sure that there was no pressure in the cylinder before you did any kind of activity on it. Now, a little bit on troubleshooting. As I said, we can spend more time with you if you think that you would get value out of having an additional troubleshooting. I could spend 30, 40 minutes just on troubleshooting alone more. But some of the common things are like relief valves. So you have customers who would complain about the noise of a relief valve. You know, this figure on the far left here, I want to make sure that you're using the quietest relief valve that's out in the market. That would be the Generate LCV, which Ratterman calls the LPR, liquid pressure relief valve. It's the quietest because not only does it meet the dB ratings, but it has a machined poppet in there that would give you a warning, if you would, that the cylinder relief valve is about to open and relieve pressure in the cylinder, that you would hear a whooshing noise that would indicate that this is about to open. It would slowly increase in amplitude of noise, and then the poppet opens and relieves and resets. The other designs are, once it hits its pressure, bang, it opens, it relieves, and it sets. So the Generate relief valve is the OEM recommended relief valve for all manufacturers. I would first check to make sure that you're using that relief valve on your cylinders if you're not. Another common problem would be dual relief valves. You know, I understand that, you know, you wish you had the right pressure rating cylinder for every given application customer that you have out there. Sometimes you need to get greater utilization out of your assets, so you may take a higher pressure cylinder and put a lower pressure relief valve on it. That works, but you've got to be able to communicate that all the way down from the person that fills the cylinder, through the driver, through the customer service people, all the way down to the end user, so everybody knows what the anticipation is. If your customer had been receiving low pressure cylinders where he could open and use the pressure builder, but now he's receiving a higher pressure cylinder with a 22 PSI safety on it, and he shouldn't be opening the pressure builder on that cylinder, they need to know that. They need to know the valve and the valve position to when it's active or inactive. So that would be my caution and recommendation there. The other thing that people have a tendency to focus on and you know, maybe freak out a little bit on would be frost. This cylinder here that you see is a cylinder that would be drawing a heavy volume of gas out of that cylinder. Those are the coils that we talked about that are soldered in the upper region of that vessel. They're drawing extremely hard on that vessel. They're probably, you know, taking all 350 cubic feet that they can get out of that thing, out of that cylinder, maybe even try to draw more. Like I said, those coils are soldered to that outer shell, so it's going to, those coils are being fed the cryogenic liquid. It would transfer that cold to the outer part of that cylinder and can build up a layer of frost. That's perfectly normal for a heavy draw gas use cylinder look. The upper right here would be when you have the pressure builder turned on. You've got that bottom 12 to 15 inches on the cylinder. Those coils down there are the pressure building coils that are building the pressure, flowing the gas through the regulator, building pressure on that liquid, pushing down on that volume of liquid. That's a perfect normal look to have those pressure builder coil frost appear in the bottom of the cylinder. That can actually, even if the customer turns his cylinder pressure builder off, which he should every night when he's not using the cylinder, turn the PB off just to preserve the volume of liquid. It's perfectly normal to see that frost remain, and might even remain there overnight. The lower right would be, as I said, that plumbing that flows through the cylinder, goes through that knuckle in the center of the cylinder. That tubing can draw that cold from that liquid to the outside. That's not all that uncommon to see that tubing frost up, you know, following a fill. and movement of the cylinder, that would be what I would consider more of a normal frost following a fill. Now this frost that you'd see here on this photo on the left would be what I'd consider excessive frost buildup. The cylinder may continue to work perfectly normal. You'd have to talk to your customer about it who's complaining about it. This could be a couple things. It could be it's a medium pressure cylinder, which you would indicate by the color coding of the float rod cover here as being blue, which is medium. But this could have been with frost like that, it could have been a DOT 4L100 cylinder that maybe had a 22 PSI relief valve on it. You filled it with 80 to 100 PSI liquid, that cylinder would need to stabilize. That safety could be going off with such frequency that it frosts over. You could pour warm water on that. You could hit it with a heat gun and defrost that and try to get that relief valve to set. More than likely what this is a leaky connection here at the float rod area, or it could be this LCCM, the joint where that LCCM seals up against the manifold, that could be leaking, and that would build up that level of frost. If the customer can use the cylinder, let him use the cylinder, but then flag that. So the next time it's there, have Jesse's technicians pull that float rod and replace the O-ring in there and retorque that down, and hopefully that would resolve the problem. This cylinder here on the right would be what I'd consider a classic bad vacuum look. You have that liquid that's in there. If it loses its vacuum, it's lost. It's significantly lost the insulating value of between that inner vessel cryogenic liquid and the outside temperature, and it is just boiling off. It's like you poured that cryogenic liquid into a bucket, and it's just sitting there bubbling and boiling off. The cylinder will build pressure. You can watch that gauge rise and build pressure. You can open up that vent safely in a direction where it's not pointing in somebody's face, and you can vent that cylinder down and lower that pressure, and you close that vent, and you just watch the gauge build pressure right back up again to where the relief valve is going off. That is a classic bad vacuum look, and that would require the cylinder to go out and get re-vacuumed. And brand new cylinders that we sell here from Taylor Wharton, we guarantee that vacuum for 7 years. So anything that happens with that vacuum in the first 7 years, it's being repaired under warranty anyway. So, and that will conclude our session for the day. Should any of you have any questions, there's my email, there's my mobile number. You can call and ask me questions. The 1-800 number at the bottom is for Radaman. Please feel free to call in Radaman and let them know, if you'd like some other type of training or have any information on how to repair a liquid cylinder that you can do on your own. We'd be glad to try to help you out.